there's always somebody walking towards a light and a shadow changing, right? If you're walking, I guess you can't really walk towards the sun and watch your shadow change because it doesn't happen that often. But if there was a spotlight on you, depending on the way that you're walking, your shadow's either getting bigger or smaller. And so the question is, well, when I'm walking at a certain rate, how fast is my shadow getting bigger? And it seems like wherever you study related rate problems, there's always one with a shadow. And these are similar triangle questions. So a spotlight shines on the ground. No, shines on a wall. So we got a spotlight on the ground. We got to draw it pretty here. Here we go. There's our spotlight. Get some nice rays of light coming from there. Oh, nice. So there's our spotlight on the ground. Shines on a wall 10 meters away. So we've got 10 meters away is a wall. That's a pretty wall. Oh, I like it. Okay. Now, for whatever reason, a 2-meter tall man decides to walk towards the wall at a constant speed without stopping. Hopefully he realizes the wall is there. There is a light on the ground for that very reason, to warn people not to run into this wall. That's probably why that light is there. So here we've got our 2-meter tall person walking towards the wall at a rate of 1 meter per second. What that does is that creates a triangle, and you can imagine a big scary shadow. Ooh. Right? There's the big scary, ooh, that's even scarier. How did I do that? There we go. Big scary shadow on the wall. And that shadow this is probably the reason this is a smart man who knows that shadows are scary, but what would you do to scary objects? You normally run away from them, but he is so smart, he starts running towards the wall to make the scary objects smaller. When he hits the wall, the shadow will go away. So he's a very smart, maybe not quite so smart man, running towards the wall to make the shadow go away because he's scared of it. Okay. We need to introduce some variables here. We want to find out how fast the shadow on the wall is decreasing. So we need to make that a variable. Since that's a vertical one, I'm going to make it y. So what we're trying to find is dy dt, which means that y is a function of time. He's walking towards the wall at a rate of 1.2 meters per second. So we need to introduce that most likely we'll want that to be our dx dt. And looking at our diagram, we can call this distance right here the distance that the man is away from the wall, because we want to find out how fast it's decreasing when he is 3 meters from the wall. We can call that distance x. If I call that distance x, what is dx dt? We want to write 1.2, and that's very close to the right answer, but it's not quite the right answer. What's happening to x? Is x getting bigger, or is x getting smaller? It's getting smaller. So it's going to be negative 1.2 meters per second, which tells us as well that x is a function of time. We know if this is x, then this part over here is 10 minus x. And the height of our man is 2. And this is what makes these shadow questions the hardest, is now you have to take that information and make an equation. The 10 minus x would be this part here, because this part is x. And those two together have to make 10, because the spotlight is 10 meters away from the wall. So we want to find out something when x is equal to 3. We want to find out what dy dt is. And he's going at that constant rate of negative 1.2 meters per second. Well, it depends where you put his face. Let's put his face right. He's scared, right? So he's like, so he's definitely looking at the wall at this point, right? But he's probably read somewhere that shadows only attack if you run away from them. And so if you run towards your shadow, it'll probably go away. So the key to making this equation is to recognize similar triangles. Whenever you have a triangle like this with two right angles, there's a right angle with the guy here and a right angle with the wall. We're assuming that none of these shapes are bent. Then this triangle made with the man in blue is similar to this big triangle made with the wall in green. And what do we know about similar triangles, which we've already seen? The ratios are going to be the same. The ratio of, I'm going to say, the base to the height has to always be the same. So no matter which triangle you take, if you take the base and divide it by the height, or vice versa, the height divided by the base, you should get a constant number. And this is basically the whole idea about trigonometry, right? The opposite over the adjacent. This angle where the spotlight is doesn't change. That spotlight's angle doesn't change. And what do we call the ratio of the opposite over the adjacent? That's just your tangent ratio. And it doesn't matter how big or how small that triangle is, that tangent ratio always stays the same. And so that's the idea of similar triangles. We know that the base over the height for both of those triangles has to be the same. Well, if I look at my blue triangle, my base is 10 minus x. My height is 2. If I look at my green triangle, my base is 10. My height is y. Those two things have to be equal. And now I have a relationship that has both y and x in it. So I can take the derivative, but before I take the derivative, just looking at this, I might want to rearrange things a little bit. You know, I could multiply to get rid of fractions, or I could distribute this 2. What would you want to multiply out and have to use a product rule in derivative, or do you want to simplify both sides and just use exponent power rules? You want to do both just to see what it looks like? So one way you could deal with this is if I multiply both sides, well, I get 10y minus xy equals 20. And I'll just draw a line here. You can decide which way you like better. Or I could simplify both sides, and I could say this is 5 minus 1/2 x equals 10y to the negative 1. Are you okay with how I simplified both sides? So if I took the derivative with respect to time of this one, or and later I'll do the one side first, but I could take the derivative with respect to time of either of those equations. What happens on the left? The derivative of 10y is 10 dy dt minus, what's the derivative of xy? It's a product rule. So I'm going to put brackets here because I'm subtracting. keep one the same, derivative of the second, plus keep the other one the same, derivative of the first, and the derivative of 20 would be 0. So now what do I want to find? I'm wanting to find dy dt. So I would have 10 dy dt minus, at the point when x is 3 dy dt plus, at the point when x is 3, we need to know what y is. So now we have to go to our situation and figure out what y would be at that time. So here's our triangle. When this is 3, this would be 7, and this is 2. What is this height here? Well, we know that that ratio has to be true, so 2 over 7, wow, that's a fancy 7. 2 over 7 has to equal our question mark, which is our y. Maybe I'll just use the letter y, over 10. So at when x is 3, y is 20 over 7. So we would have 20 over 7, and dx dt we already know is negative 1.2 equals 0. Multiplying this out, simplifying things, we're going to get 7 dy dt is equal to 20 over 7 times a negative 1.2 times a negative. Move over to the other side, will be negative. I'm going to change 1.2 to 6 over 5 just to make calculations a little bit easier. And then we get 24 over 7. Divide by 7. And dy dt is negative 24 over 49. What were our units? Meters per second. So he's running towards the wall. He's seeing progress because the shadow is shrinking at about 0.5 meters per second. Okay? So 3 meters away from the wall, he's realizing things are looking good. My shadow is decreasing. He's gaining confidence. He's going to stay the course. What do we've got? About another, just under 3 seconds left before he hits that wall, right? Because he's 3 meters away, running at 1.2 meters per second. Now, that was using the equation on the left. Using I'm just going to, this is important information, so we'll keep it there for later. Using the equation on the right, if you took the derivative with respect to time, I'll finish it up. You guys can go if you like. You get negative 1/2 dx dt.
Just a reminder for all students that are interested, the Big Band dance tickets are available.
Negative 10 y to the negative 2 dy dt. You could plug in everything the same. Again, we figured out our y to be 20 over 7. So that would be on the bottom, squared, dy dt. And solving for this, you should get the exact same answer, negative 24 over 49, that way as well.